everybody. I'm really happy to be able to introduce Dr. John Deenik. Today he's going to talk to us about Hawaiian dirt. He's a professor in TPSS, Tropical Plant and Soil Science, and he teaches a soil science class, which by all accounts is the most life-changing experience ever. So if you're hunting around for a fun class to take and want to learn something about soil, consider that class. I have a big appreciation for Dr. Deenik as well, because he did 4 years Peace Corps in Nepal, 5 years Peace Corps in Nepal. Talking about getting lost. Where I spent some time too. So he speaks fluent Nepalese and some English as well. He's going to tell us all about the wonders of Hawaiian dirt.
Okay, aloha kako.
Aloha.
Bea, mai kai. Can you hear me? I won't do it all in Hawaiian. I'm learning Hawaiian. I'm a student. 202. Anybody taking Hawaiian 202? Not so easy, huh? Like, my guy. Okay, so I'll do my best to speak. I have to stand down here, which I feel a little more comfortable down here than up there, because I got to switch the slides. Yeah. So we're going to take a little poo-poo entry into soils with a focus on Hawaii. Yeah. I see some faces. I saw an old student of mine from the past. Where is he? Tim. Yeah, he's up there. He took the soils class a few years ago, so he could probably come up and give the lecture too. But we'll spare him that, yeah? Okay. So, just a little poo-poo to get us started. 3 soil pits from Oahu, right from this island. They look the same?
No.
Pretty different, yeah? So, soils are different, one from the other. You probably knew that, but you're going to get a better appreciation for that. And one good indicator of soil difference is color. Yeah, color. Color can tell you a lot about a soil. What does that tell you?
It's like iron.
Iron. Good. Oxidized iron, right? Iron oxide. Hematite. Yeah? This one's iron too, but it's a little more yellow, yeah? Goethite, different kind of iron, still iron. And this one has some iron too, but really the black is coming from manganese.
Or manganese.
Manganese, yeah? Ho'olau soil, Lualua. So all of these valleys right here on the west side of this island, who's from Waianae? Waianae, very good, yeah? So Lualua is the most important soil of these amphitheater valleys on the west side, dry. And then these red soils tend to be at the higher elevations, central Oahu, east Kauai. Yeah. Good. So we're going to spend a little time. Why should we care? We know soils are important, right? But we'll get a little bit of details now. Soils are different one from the other. Why are they different? Can we explain these differences? And something about soils and land use. We don't have a lot of time, right? 50 minutes, so we're going to try to cover a bunch of different things. But I think it'll open up some thought for you all. The central resource. Yep. Like air, water, and sunlight, life depends on soil. Not entirely, but without soil, we would not see what we see today around us. It's in the center here because it mediates all of the other components of our terrestrial and atmospheric world. Yeah? There's a transfer of gases between soils and the atmosphere. Right now, it's pretty important, right? What was going on in Paris earlier this year? I guess it was last year. Yeah? Climate change conference discussions, right? Soil plays a critical role in gas emissions. How we interact with soils depends on which gases are released and at what rate. So land use change has a tremendous impact on climate because the way we treat soils impacts greenhouse gas emissions. Water. Yeah. Soil is a big sponge. Yeah. Basically, that's an easy way of thinking about soil. Soil stores water. It stores a lot of water. Some soils store much more water than you might imagine. We have soils on the windward side of Kauai formed in volcanic ash that can hold 200 to 300% water by weight. Wow. Huge capacity to hold water. And that's a life-giving property, correct? Yeah. Do you see a lot of plants growing on basalt lava flows? Not yet, right? Rocks don't hold water like soils do.
Or here can grow on lava flows.
Very good. These are pioneer species. Exactly. Very important. But the lava flow is only little cracks where that ohia finds its home, yeah? Very good point. And right around that ohia, you'll find soil forming. Good. Biosphere, so life, right? Soil is home to life, but it also supports life. We see the plants, but it's also the home. Organic matter, nutrient cycles are all driven by soil. And of course, interactions with rocks. Rocks are the parent, but the soil puts elements back through the rocks. So, very quickly, 6 functions. Some of them were pretty obvious to us. It's a medium for plant growth. Yeah. Why does soil promote plant growth? What are some of the properties of soil that allows it to promote plant growth? Name a few. Water supply, very good. We mentioned that before.
Holds nutrients.
Nutrient supply. Anything else?
Holds the plant in place.
Very good. It's an anchor, yeah?
Foundation.
It holds the plant in place. We know that shallow soils, trees can fall over in shallow soils, right? Why? Because their roots are not as well established. Good. So those are 3 that you knew already. Very nice. Okay? It's a habitat for organisms. Immensely diverse. Huge amounts of life in very small quantities of soil. Yeah? 1 gram of soil might house over 1 billion living cells. Can we see them?
No.
No. But now we have tools. Dr. Amen does his work with these tools, genomic tools that allow us to now understand the complexity. And this whole concept of the soil food web is immensely complex, and I think is at the forefront of our discipline, is understanding how these organisms interact with each other, plant roots, and other organisms to promote life-giving processes. When I first started studying soil science, we had no clue of these complexities because we didn't have the tools yet to really unravel how much life is beneath our feet. It's a recycling system. Much of my work deals with recycling waste. Yeah? I work with farmers in Pohnpei. How do we get their pig manure? They wash it down into streams, polluting their streams. How does that pig manure help them rather than act as a hazard, a polluting source? Well, we build on the concepts that we know from soil, composting, right? It's a soil process that goes on every day, out in fields, out in the forest. And we build upon this. Water supply and water purification, we mentioned that before. Without soil, we can't hold water to promote life. Water purification is a little bit more complicated, but nonetheless just as important. As water moves through soils, contaminants can be adhered to soil components, especially clays and organic compounds. So it can purify and keep our water clean. There's been over 100 years of intensive agriculture on central Oahu, correct? What were the 2 primary forms of intensive agriculture in central Oahu? Sugar and Pineapple. Think they used a lot of nitrogen fertilizer? They did, for a long time. Do we have nitrate in our groundwater as one of our problems? No. But you would think after 100+ years of intensive nitrogen fertilizer application in many parts of the Midwest, the Po Valley in Italy has a serious nitrate problem in the groundwater due to leaching. They use nitrogen like we do here. We're blessed by nature, in one sense. That deep soil profile of that red soil I showed you just earlier, in the subsoil, those clay particles have positive charge, meaning their clay surfaces have positive charge. What's the charge on a nitrate ion?
Negative.
Negative, right? So as a nitrate ion moves out of the surface soil, because of over-application, it didn't get taken up in the plant. What happens to it as it moves into that red subsoil?
It binds to the soil.
It doesn't bind, but
Creates
it's
a-
held back. It's delayed. Its movement is delayed because it has a positive charge, it has a negative charge, and it gets held by anion exchange reactions. And so that delay plus a deep, very deep subsoil has protected our water resources. Now, that doesn't mean we can just mismanage agricultural fertilizers, correct? Nonetheless, that's a peculiar property of tropical soils.
If it only delays it, does that mean it will eventually get into the groundwater?
Well, that's a very good question. We, back in the 90s, we got a little bit of money, well, it was quite a bit, and we dug very deep boreholes. And we saw bulges of nitrate in the subsoil. And it's not moving, okay? And because it's delayed, it attenuates the effect, right? It's not these big pulses of nitrate moving right through the profile into the groundwater. It goes slowly, so it's diluted, right? That aquifer is huge. Good question. We spoke a little bit about this, soil as a modifier of the atmosphere. So soil stores organic matter. You know? Soil stores organic matter as carbon and keeps it in the soil. Disturbance can release it through decomposition. CO2 can go up into the atmosphere and acts as a greenhouse gas, correct? How we manage agricultural fields, especially with regards to nitrogen fertilizers, also has a very important impact on atmosphere. What form of nitrogen is particularly scary when it comes to greenhouse effects? N2O, did somebody say that? Yeah? So N2O is the product of denitrification, right? So when you denitrify nitrate, or when nitrate becomes the electron acceptor in a waterlogged or poorly aerated soil, that nitrate goes up as N2O. And compared to CO2, it's more powerful or less powerful as a greenhouse gas? Much more powerful, right? In fact, 300 times more powerful. So how we deal with nitrogen in soil is very important for our future. And then lastly, it's an engineering medium. I switch this picture around every now and again. I had direct contact with soil as an engineering medium because before I went to Nepal, I spent 2 years in Cameroon, in the tropical rainforest of southern Cameroon, and our house was made of clay. Yeah? It was bamboo or wooden frame and clay packed in there. So very important engineering medium, has been for many, many centuries, right? Building materials, foundations. Yeah? Anybody here live in South Oahu, Honolulu, Poikai, New Valley? Yeah, all of those valleys. Have you heard of, have you seen sidewalks kind of buckling and moving about, and heard of houses sliding off their foundations? Yeah, that's because there's a particular soil over there called a vertisol that inverts itself. That's why it's called a vertisol. And because it's inverting itself, it's inherently unstable. And if you're not careful and you build a house on it, not a good foundation, correct? You could lose your house. But if you know the property of that soil, you can make arrangements, engineering arrangements. This is what? What is this area?
Downtown.
Downtown, right? Makiki, Waikiki, right? What was it 500 years ago? It was a wetland, right? Right. Marshy. In fact, a lot of kalo, rice after kalo was grown in this area. How did they put all these buildings there?
The White Canal drained it.
Okay, drainage. So they drained it. But could they build right away? A lot of fill, right, brought in. So if you go to a soil map and you click on it and you want to know what kind of soil is there, it's going to be called fill. Okay. Next idea, I said we're going to learn a little bit about soil diversity. Soils are different one from the other, yeah? Remember that? So, here's a view of the globe, yeah? And each of these colors represents a unique type of soil with a funny looking name. Don't worry about the name. If you take my class, unfortunately, you'd have to learn it. And some of you probably still remember some of these names. But the name tells us quite a bit. We're going to focus on a couple here just to give you a little introduction to soil classification. Yeah? We can classify soils based upon observable and measurable properties. Yeah? Similar properties. Measured meaning pH, clay type, organic matter content, sandy or not. Yeah? So we use these types of observations, measurements, to place soils, group them into similar soils of similar properties get placed in the same group, like any classification system. This is the USDA soil classification system. It's just called soil taxonomy. You think it's the only one in the world?
No.
No. Right? You think France has a soil classification system?
Possibly.
Absolutely. What about Russia?
Possibly.
Yes, it does. What about Switzerland?
Possibly.
Yep. So we have many classification systems because we're nationalistic. Yeah, we wave our flags and wave them around. There is one universal classification system by the Food and Agriculture Organization under the UN. Okay. So there is one that's widely adopted, but each country basically uses their own. This system, however, tends to be adopted most widely by scientists of the world. So you might read a paper of soil scientists from Zimbabwe doing a study on soil fertility. They will typically use this system to tell you what soil they were working in. So it's become one of the most common languages for the science, but not the only. Nonetheless, let's get a feel of this. See, the colors represent each of these different. Anybody speak Latin here by any chance? Yeah, you do? You recognize any words up there? Sol. It's not a word.
Sol.
Sol. Yeah. Okay, solum. That's Latin word for soil, yeah? Okay, so all end with sols. Any other part of it? Mollis? Anybody heard of mollis? Soft. Okay? So a lot of these come from Latin. Nonetheless, let's look at this one. Green color, yeah? Green, green, green. All a similar kind of soil. Now, within the mollisol group, there are many individual types of mollisols, but they all share some key properties. Yeah? What might be similar about those areas of the globe that create soils of similar behavior and properties? Pardon? Climate, okay. Temperate, yeah. Temperate, good. Yep.
What grows there?
What grows there? Very good. Well, tell us, what grows there?
In the greens?
Yeah.
A lot of crops.
Well, now a lot of crops, but let's think back maybe 5,000 years ago. before the population had completely transformed these areas. Let's imagine 5,000 years ago, you fell right here, or you fell right there, or you fell right there. What grows there? What might you have seen for as far as the eye can see? Grasslands. These are the great grasslands of the world, right? In this part of the world, we call them the prairie. The prairie, right? They are plains, but they're really prairie, right? Here we call them the
Pampas?
pampas. Good. Somebody who's taken some Are you from Latin America?
No, but I have taken geography.
You
class.
took geography. Gosh, that's amazing, yeah? Okay. And what do we call, what's this?
The steppe.
The steppe. You see, it's good to take a geography class once in a while, yeah? You didn't learn that back in 10th grade or something? Not anymore, huh? I guess. Okay, that's okay. Nonetheless, the steppe, the pampas, the prairie, grasslands. They can be flat, but they're typically undulating. They can be slightly hilly, right? You've seen these landscapes before. But grass is the key driver here. Describe to me grass root systems. Fibrous. Very good. They're dense, yeah? Some are really dense. Who's tried to dig up a guinea grass bunch? Yeah? Were you successful? Pretty tough, huh? Lots of roots. What do those roots contribute to that surface layer? Organic matter. Lots of it. So these soils are characterized by a dark, organic matter, rich, fertile surface layer. And it has to be a certain depth to meet the classification of this mollisol. Okay, so there are criteria that have to be met. Yeah? To be a mollisol as well, you must have at least 50% base saturation, which is a fancy way of saying rich in calcium, magnesium, potassium. Are those important elements? Yeah, they're essential plant nutrients. Okay? Soils that are deficient or low in calcium tend to be less productive than soils rich in calcium. Okay? Good. So we see that these mollisols, the driving factor is the presence of grasslands over extended periods of time, have formed a similar kinds of soil. Now within that mollisol group, there are subcategories. We don't have time to get into that, but they're not all the same. Not all mollisols are the same. Some are deeper than others. Okay? Some are sandier than others, but they all share three main characteristics. High organic matter in the surface layer, rich in calcium, magnesium, and potassium, and productive. One of you said, lots of food. That's right. Now, if you were to fall out of an airplane by mistake and land in Illinois, what would you see?
Farmland.
Lots of
Farmland.
corn and soybeans. Yeah? What about if you fell out of the airplane into the Ukraine? You would see lots of
Barley.
barley, wheat. Yeah? Okay. Good. One more soil before we move on. Look at this red soil. Yeah? Let's look at this red soil. Anybody want to guess what oxy might refer to? Oxygen's a good guess, but it would, if it were oxygen, it would be OXY. Yeah? Oxide. Okay, so iron oxide, aluminum oxide. Are these easily soluble materials? Does iron oxide dissolve? No, it's the end of weathering, right? We're going to get to that concept in a minute. Yes, these oxysols are rich in clays like gibbsite, hematite, goethite, which are all aluminum and iron oxide minerals, clays. Yeah? Here, I was born in Colombia, so but if you go to southern Colombia down here, what's here? If I were to fall out of the airplane here, that's the theme of today, yeah? If I landed right here, what would I see all around me? I was a Peace Corps volunteer right about there in southern Cameroon. When I would look out my class, I'd look out and what would I see?
Tropical rainforest.
Tropical rainforest, yeah? What's the climate like?
Hot, humid, wet.
Hot, humid, wet. Good. Okay? So, because you know it's hot, humid, and wet, you have a dominating mineralogy of iron and aluminum oxide. What process is forming these soils or has led to the formation of these soils? Extreme weathering. Extreme weathering, which means that soluble components have all leached away. So these soils tend to be very low in calcium, potassium. Magnesium is a little bit different. It depends the parent material. Our oxasols here in the Hawaiian Islands still have relatively large amounts of magnesium because the basalt rock is magnesium rich to begin with. Nonetheless, these tend to be classified or thought of as relatively infertile soils, especially in comparison to mollisols. Now, when I came to soil science a little bit late. I was an art history major. Yeah, remember a few years ago our esteemed president said some disparaging remarks about art history majors? Did you catch that?
I don't remember.
No, that's okay. Anyway, I came to soils late, and when I learned about oxasols, and my professor said, oh, they're infertile soils, low nutrient status, and started describing these, and they occur in the tropical rainforest, and I kept thinking, God, how can that be? When I looked out my window of my classroom in Cameroon, it only looked fertile because there was huge trees everywhere. Very productive, these forests. Where did they get their nutrients from? The clay, actually, if you dig down into that red, you saw that first picture of that red soil, if you measure nutrients there, is very low. In some cases, trace calcium. You can't even detect it with our instruments. How come the forest is growing so well?
Because they're really, I think, according to one of my geography classes, the trees in tropical rainforest are really efficient at sucking out the nutrients, so they're already sucked out of the soil. They're in the trees already.
Okay, so they're good at scavenging for nutrients in the soil, but you keep scavenging, you're going to exhaust that reservoir of nutrients, correct? Right? It's not an endless source. What's part of that soil is contributing to fertility? The organic matter that builds up in the surface layer as that tree drops its leaves, falls down, drops branches, all of that material recycles nutrients back into the system. That's why many hundreds of years ago, peoples of the tropical forests were able to survive by carefully slash and burn agriculture, correct? They didn't cut everything down, but they cut some areas in the forest, utilized that organic matter rich surface layer to grow their peanuts and bananas and yams and sweet potato for a couple of seasons. Then they realized, okay, the nutrient levels have been removed. They left it. The forest grew back. 50 years later, you wouldn't even have known. You could go back and do the same, yeah? Okay, so organic matter plays a key role in the fertility of this naturally infertile soil. Okay, good. We don't have time to go through all of them, but throughout the lecture we'll come back to some of these names, yeah? So, look at Oahu. It's a really tiny island. Very small island. You know, you can drive around it in a couple hours. Yeah? Even if, you know, I walked a lot in Cameroon. In a couple of days I can walk from Makaha, where I live, all the way around. In fact, when they do the makahiki, every now and again they'll carry the lono and walk around the island. You've heard of that, correct? Yeah, not that far. Look, 9 of the 12 soil orders. 9 of them. Yeah. Let me go back a minute. Yeah, because I'm not sure how I do that. Let me not. Kansas. Anybody been to Kansas? That's pretty big. I had to hitchhike across it a few years ago. That was rough, man. You might only find 2 or 3 soil orders in all of Kansas. Yeah. Why so much diversity on this tiny island? We'll get to that in a minute, but think about that because I'll ask you. So, soil formation. What drives soil formation? Well, what's this?
Lava.
Lava, which would be the parent for us, yeah? In Yosemite, would lava be the parent? No, a different type of igneous rock, right? You know, those plutonic extrusions, yeah? Good.
Right.
So we have the parent, we have, let me go quickly here, parent, then we have to consider how old is the landscape? Has it been around for a long time? We have to consider what kind of climate exists that acts upon the parent for how long. So you can imagine a very dry environment would have a big effect on the parent rock. Not much, right? Because water is a key transformer, a key driver of chemical reactions. Okay, so climate, very important. And then what kind of life is there? As we mentioned before, those green soils that we call mollisols, the biota, the grassland was a key driver in differentiating those soils from others. Yeah? And then the lay of the land, the topography. So these are the 5 state factors that interact with each other to produce different kinds of soil. We also think of additions. Water is an addition. So as you add water to a system, it promotes chemical reactions, promoting weathering. Transformations, the key transformation we're talking about here is chemical weathering. But we also have decomposition of organic matter, produces products that change the soil or change the environment. And movement of particles and water and clay components and nutrients within the profile differentiates a soil. And losses, leaching. So if we think back to the mollisol, that prairie soil, grass, key component, yeah, grass, roots add lots of carbon, lots of organic matter, yeah? And there are transformations within there to weather the primary minerals into clays. So, rather complicated actually, but we've made great strides in understanding how these processes and state factors interact. Yeah? So keep these in mind as we move forward. Yeah? Let's look at time real quickly. We have a perfect laboratory here in the Hawaiian Islands to look at time and soil development and soil diversity. Perfect laboratory, wouldn't you say? You go from a very young landscape to a pretty old one. What's the difference between Hawaii Island and Kauai, let's say, or Niihau?
Size.
What's the time difference? You know, the age difference.
About 4 to 5 million years.
There you go. On average, Kauai is about 5 million years old, plus or minus. Yeah, you had a geology lecture, I'm sure, where you had a little bit of this hot spot geology. Yeah, and the Big Island is forming right now. Do we agree? Kilauea is producing new parent to be weathered at some time in the future. But we'll see in a minute that Kohala is quite a bit older than Mauna Kea or Mauna Loa, right? Kohala volcano is the oldest volcano on Big Island. About what? 400,000 years old? Is that about the time scale you heard from Dr. Rowland? Is that who came and spoke to you? Dr. Stout, even better. Yeah? Okay. So, on a relatively young island, we still have some soil diversity. All this, not blank area, but non-colored area that says other, what is that?
Rock.
Rock. Lava flow, or in the case of Mauna Kea, when you go up here, Mauna Kea, Mauna Loa, what is it?
Snow.
Cinder. Now you've seen the cinders? Yeah, some are big, but it's cinder, yeah? And there's no soil yet. Okay? Yeah.
So is this? Did you show us a different island before that had 9?
Yeah, yeah.
That was Oahu. and
That
this
was
is
Oahu.
Hawaii?
Yeah, we'll get to Oahu again. Good point though, right. Now we're at Big Island, Hawaii Island, the youngest of our 8 main Hawaiian islands, correct? Yeah, the youngest. And if you talk about Kohala, it's about 350,000 to 400 to maybe 500,000 years old, correct? Yeah? Now, why do I say that? Is because there's a standard error around their time measurements, yeah? Whereas if you go to Kilauea right here, it's forming right now. We're getting new lava rock is forming. The dominant soil type on the Big Island is this purple color that we call andesol. Andesol is a soil that is associated with young volcanic activity areas. Other places around the world with dominant andesol landscape would be the Cascades, around the Cascades in the Pacific Northwest, parts of Japan around their active volcanoes, New Zealand, North Island, Indonesia, parts of Central America, Costa Rica. Yeah? Wherever we've had relatively recent volcanic activity, you form a soil that is rich in a particular type of clay that we call allophane. That's the dominant factor of an andesol. These are non-crystalline clay minerals. Now, andesols can be very fertile, productive soils, depending on what kind of climate regime they're under. Let's take a look here. If we look at the drier side of the Kohala and Mauna Kea area, very fertile soils. The wetter side, much less fertile. We'll look at that very in a little bit more detail in a minute. Okay? So Big Island, still quite a few soils, 1, 2, 3, 4, 5, 6 soil types, okay? Which is quite a lot for a small area like this. And age is a driving factor. Older, you see there's more soil types over here. And then here in Kona, you can see some small areas of this mollisol. And that's different aged lava flow. So this mollisol area has been exposed to the atmosphere for longer times. If we were to look at a lava map and age distribution, there were many different lava flows, yeah? Different age groups. Here we are, Oahu again. Now we're at 2 to 3, even maybe, you know, the Waianae volcanoes can as much as 4 million years old. In fact, some of the newer research says that out here towards Kaena Point, they may be even as close to Kauai age, so quite old. But nonetheless, with time, you get much more diversity. Yeah? So now we go up to 9, and then you can imagine that the next slide showing Kauai, we have 10 of the 12 main soil types on the planet, and this is in part due to the age. There are other factors which we might have time to cover, but you have andesols up in the wet area of Kokee. You have mollisols, the fertile grassland soils on the dry western side of the island, and then you have these tropical oxysols, iron-rich, depleted soils where there's high rainfall. Windward Kauai has a wet place. Yeah? Rainfall, leaching, loss of soluble components. What remains behind? Oxides of iron and aluminum. Okay, let's look at climate now. Let's take a quick moment to look at it. Very specific, another beautiful natural laboratory. Perfect experiment to help us show the key role that climate plays in differentiating soils. This is the pastures on Kohala Mountain. Yeah. Anybody's been out there? Really nice, really nice area. Okay. There was a really nice study done now more than 10 years ago by a geochemist, soil scientist. Oliver Chadwick wrote a really nice paper describing the effect of rainfall along a rainfall gradient over here in Kohala. The same parent. So here's the Hawi lava flow. I think it's about 400,000 years old. Or, yep, I have to go back. I'm not as good at remembering things as before. And you have down at the coastline. Who's been down at the coastline and the low elevations out in Kohala? What's it like? Hot and dry, windy. Yeah. Do you think you get a lot of water movement through the soil? No, evapotranspiration is dominant. You lose most of your water, right, to the atmosphere. Okay? So is water moving through that profile readily? Only on large storms, once in a while. But not very far away, within 10 kilometers, you could walk this transect in a day. You get up to the higher elevations, and you get up to 3 meters of rain. 3 meters, 9 feet of rain a year. So you go from basically no rain to a lot of rain in a very short distance, and most of the other soil forming factors are maintained constant. The parent is the same, yeah, the same lava flow, so the age is about the same. Yeah. There are some influences from these pu'u, which are we have to also consider, but nonetheless, on average, the age is the same. Biota is a little bit different. Well, that's climate-driven, right? This is a forest environment, and this is grasslands. And down here, even less vegetation. So vegetation isn't quite held as constant as one would like it. Nonetheless, we will see a nice impact of climate as we move up. So here's how rainfall increases with elevation, yeah? And as you go above mean water, okay, so as the rainfall increases, the availability of that water, meaning the water in the soil increases. And the key point is here, you have evapotranspiration dominating, meaning water is leaving the soil, not moving through it as the dominant factor. And above this 1,300 millimeters of rain, you have surplus of water, which means water is leaching, moving through the soil profile daily, almost, yeah? And so that water, as it moves through, and the presence of that water drives what kinds of reactions? Weathering reactions, yeah? So the transformation of the parent to secondary minerals, clay minerals. So we have a leaching environment at the higher elevation, and here are some of the effects of that. At low elevation, low rainfall, pH is high. pH is a measure of acidity, right? High pH, low acidity, alkalinity, or near neutral. For plants, do plants typically favor high pHs or low pHs?
Low.
Well, they have both, right? Some are tolerant of acidity and others are not, yeah? Many food crops don't do so well in very acid soils. Taro, for example, vegetables. Nonetheless, as rainfall increases, pH maintains, and then when you get to that 1,300 millimeters of rainfall, you go from a water deficit condition to a surplus. A surplus means what? Leaching, and the pH plummets. Why is that? The soluble, alkaline driving components are leached out. What's left behind are acid-forming aluminum compounds. And so you go from near neutral very quickly to very acidic environment. Weathering. Okay? Similarly, we said earlier that a soil supports plant growth because it can store nutrients. I think my friend here told me, yeah, a soil can make plants grow. One of the reasons is that it's able to hold nutrients. The ability of a soil to hold nutrients is named cation exchange capacity. That means negative charge associated with the clay minerals that can hold important essential elements like calcium, magnesium, potassium, zinc, copper. Yeah? When the colloid system has a negative charge on it, it holds nutrients. At low rainfall, less intense weathering, you have relatively high cation exchange capacity, meaning that soil can hold back plant nutrients. But as rainfall increases, you reach a plateau, and then it drops. You see the drop is at a similar rainfall, yeah, around 1,300 to 1,500 millimeters. And when you get up into the high elevations where high rainfall exists, that soil has a very low capacity to hold nutrients. Yeah? Why? The minerals, the clay minerals that impart negative charge to that system have been weathered out. And you're left behind with iron minerals that don't have that capacity. And I mentioned before that a mollisol is defined by high base saturation. Y-axis base saturations in the drier environments, high base saturation. As you increase rainfall, you get this, again, same shape, like a threshold. Yeah? And it plummets. And at the higher elevations with high rainfall, base saturation goes to very low. So, this very narrow area, you see a big change in soil properties due to weathering, presence of water. High rainfall areas, the water has leached out all of the soluble components. This is considered an infertile soil. Now it produces a forest. There's a forest there because of organic matter and microbial interactions. These are very fertile soils, lots of calcium, lots of phosphorus, lots of potassium. Now the most interesting is that our ancestors, here's a view from a pu'u, one of those cinder cones in Kohala. And as you look out across the landscape, what do you notice dramatically? Stands out pretty clearly. What are these? Just natural, well, I don't know, maybe ripples from I don't know what. No, these are ancient walls. So terraces. In fact, this is the Kohala field system. Yeah? So starting around, they think the archaeologists have gone and done some dating, starting somewhere around the 1600s, or maybe a little earlier, up until Kamehameha's days, the 1800s. This was a vibrant agricultural system, dryland system. Lots of crop production in this area. Now, these walls, these archaeological artifacts of intensive agriculture only exist in a narrow belt on the Kohala Mountain. Which belt do they exist in? Where you match rainfall and fertile soils. So here's that Kohala field system. So if you go to Kohala and you walk through any one of these areas, it's mostly ranching now, mostly pastures, yeah? You will find remnants of these terraces from our ancestors who farmed this area intensively. And you will notice that it coexists in this area where rainfall is about from a little bit less than 1,000 millimeters up to about 1,500 millimeters a year. And that area coincides with the most fertile soils and where rainfall was adequate enough to support plant growth. They didn't have irrigation systems up there. It was difficult at the time. Yeah? So here's a nice, beautiful interaction of people and environment and people recognizing fertility and plant productivity. Yeah? We classify it as an andesol, but our ancestors, they didn't call it andesols. Yeah? Okay, very quickly, what time is it? I don't have much time left, do I?
You're a little over.
I'm over. See, so we didn't even get, how did it go so fast? Oh well. I won't keep you any longer, yeah?
Thank you.
Let's give him a big round of applause.
So we only went through like 5 slides. That's okay. The main thing is the Kohala field system and the interaction of weathering, parent material, climate, and fertility, and how our ancestors recognized that relationship. It's a beautiful story, actually. Thank you.